Astronomers discovered something that should not exist. A galaxy so large it defies everything we know about how galaxies form and evolve. They named it Alcyoneus, after a giant from Greek mythology. The name fits. This galaxy is a monster. Alcyoneus stretches across space farther than seems physically possible. Its radio lobes, massive jets of plasma expelled from the central black hole, extend outward in opposite directions. The total span is incomprehensible, larger than any galaxy previously known, larger than seemed achievable by any known process. To understand the scale, consider our Milky Way. Our entire galaxy, from edge to edge, would fit inside one of Alcyoneus's radio lobes, multiple times over. The jets themselves are wider than superclusters. They extend through space like cosmic rivers, flowing outward, always outward. For distances that make the mind struggle, these jets have been active for millions of years, possibly tens of millions, constantly pushing material outward, creating cavities in the intergalactic medium, carving out enormous bubbles in space itself. The energy required is staggering. The central black hole must be feeding continuously, consuming matter, converting it to energy, expelling it as focused beams that travel near light speed. This process is understood in principle. Many galaxies have jets, quasars, radio galaxies, active galactic nuclei. They are common, but none approach Alcyoneus in size. None even come close. The previous record holder was large, impressive, but Alcyoneus exceeds it by so much that it seems to be playing by different rules, as if physics allows something here that it prohibits elsewhere. The discovery was accidental. Astronomers were conducting a radio survey, mapping the sky, looking for interesting sources. Alcyoneus appeared in the data. At first they thought it was multiple objects. The lobes were so far apart, so extended. It seemed impossible they were connected to the same galaxy. But careful analysis showed the connection. Faint bridges of emission linking the lobes to the center, following the jets backward to their source. A single galaxy, one supermassive black hole, driving the entire structure. The galaxy itself, the visible part with stars, is not particularly special. It is large, massive, but not exceptionally so. Plenty of galaxies have similar stellar content, similar masses, similar structures. What makes Alcyoneus unique is the scale of its radio emission, the sheer size of the jets, the distance they have traveled. This raises immediate questions. Why this galaxy? What allowed it to grow jets so large? Other galaxies have equally massive black holes, equally abundant fuel, yet their jets are smaller, much smaller. Something about Alcyoneus is different, something we have not identified. The environment might be key. Alcyoneus sits in a relatively low-density region of space, not in a cluster, not surrounded by other massive galaxies, just alone, in a quieter part of the cosmic web. This matters because dense environments resist jet expansion. Gas from other galaxies, intra-cluster medium, these create pressure, slow the jets, force them to stop expanding. In low-density regions, resistance is minimal. Jets can extend farther, grow larger, reach scales impossible in clusters. This might explain Alcyoneus partially, but not completely. Other galaxies in low-density regions exist, yet they do not produce jets this large. Something else is contributing. Perhaps the age. Perhaps Alcyoneus has been active far longer than typical radio galaxies. Most active galactic nuclei turn on and off. They feed for a while, eject material, then go dormant. Fuel runs out. Accretion stops. The jets fade. But if Alcyoneus has remained active continuously, if its black hole has been feeding steadily for tens of millions of years, then time alone could explain the size, simple persistence creating something extraordinary. Or perhaps the jets themselves are unusually efficient. Most jets lose energy as they travel. They interact with surrounding gas, shock, heat, radiate, slow down. But if Alcyoneus's jets are somehow better collimated, better focused, they could travel farther before dissipating, maintain their energy over greater distances, create larger lobes. The discovery of Alcyoneus changes our understanding of possible structures. Textbooks will need revision. Simulations will need updating. Models of galaxy evolution assumed there were limits, maximum sizes, maximum energies. Alcyonius exceeded those limits, showed they were not hard boundaries, just thresholds we had not yet crossed. And if one galaxy can grow this large, others might exist, waiting to be discovered, hidden in survey data, missed because their size makes them difficult to recognize. Alcyonius is not necessarily the largest, just the largest we have found so far. The universe might contain even bigger giants, lurking in the data, or beyond our current observational limits, waiting for better telescopes, better surveys, better algorithms to identify them. What else have we missed? What other structures exist at scales we assumed were impossible? Alcyonius is a reminder. The universe is larger and stranger than we imagine. Our models are approximations, our understanding incomplete. There are always exceptions, always outliers, always objects that break the rules. And when we find them, when we look carefully at what should not exist, we learn, we refine, we expand our conception of what is possible. Alcyonius exists, against all expectations. Its jets stretch across space, carving territories larger than galaxy clusters, marking its presence on scales usually reserved for the cosmic web itself. And it makes us wonder, what else is out there? What other giants remain undiscovered? What other impossibilities await? Galaxies do not just grow indefinitely. There are limits, physical constraints, processes that halt expansion, prevent structures from becoming too large. Alcyonius violates these limits. To understand why this is shocking, we need to understand what should prevent it. Galaxy formation begins with dark matter, invisible mass that clumps under gravity, creates wells, potential wells where ordinary matter falls. Gas accumulates, condenses, forms stars. The process is well understood, simulated thousands of times. The simulations show a pattern. Galaxies reach a maximum size. Beyond that size, gravity becomes too weak, cannot hold the structure together. Gas escapes, stars disperse, the galaxy fragments. This maximum size depends on the dark matter halo, the invisible scaffold supporting the galaxy. Larger halos support larger galaxies, but even the largest halos have limits. Beyond a certain mass, beyond a certain radius, stability becomes impossible. Alcyonius should respect these limits. Its stellar component does. The visible galaxy is large, but normal, within expected ranges, but the radio lobes do not care. They extend far beyond the dark matter halo, far beyond any gravitational influence from the galaxy. They exist in intergalactic space, unsupported, unconfined, just propagating outward. The jets creating them are powered by the central black hole. Supermassive black holes exist in most large galaxies. They grow by accreting matter. Gas, stars, anything that falls too close. As matter spirals inward, it heats, radiates. Some of the energy escapes as jets, perpendicular to the accretion disk. These jets are magnetic, plasma confined by twisted magnetic fields. The fields act like rails, guiding the plasma outward, keeping it collimated, preventing it from dispersing. The process is efficient, but it should not be this efficient. Jets lose energy, through radiation, through interactions with gas, through turbulence and instabilities. The farther they travel, the weaker they become. Eventually, they should dissipate, merge with the surrounding medium, disappear. Alcyonius's jets have not dissipated. They remain coherent, focused, even at distances where they should have dissolved long ago. This suggests something is sustaining them, something providing energy, or preventing energy loss. One possibility is the intergalactic medium, the gas between galaxies. Usually, this gas resists jets, creates drag, slows them down. But if the medium around Alcyonius is unusually tenuous, unusually low density, resistance would be minimal. Jets could propagate farther. This matches observations. Alcyonius sits in a cosmic void, a region with less matter than average. The void would provide an easy path, low resistance, allowing the jets to expand unimpeded. But voids alone cannot explain the scale. Other galaxies in voids exist. They do not all produce giant jets. Something about Alcyonius specifically enables this growth. The black hole mass is one factor. More massive black holes produce more powerful jets, can sustain activity longer. Alcyonius's black hole is massive, but not exceptionally so. Plenty of galaxies have comparable or larger black holes, yet smaller jets. The accretion rate matters too. How fast material falls into the black hole. Faster accretion means more energy, more powerful jets. But accretion rate cannot be sustained indefinitely. Fuel runs out. The surrounding gas gets depleted. Activity ceases. Alcyoneus must have had abundant fuel. For a very long time, either it consumed an unusual amount of gas, or it consumed gas very efficiently, stretching limited fuel over extended periods. The magnetic field strength is critical. Stronger fields create tighter collimation. Better focused jets, less energy loss. But magnetic fields also dissipate, reconnect. Turbulence disrupts them. Maintaining strong fields over such distances seems implausible. Yet Alcyoneus managed it. Another consideration is the jet speed. Faster jets travel farther before slowing. They punch through the medium more effectively. Maintain coherence over greater distances. If Alcyoneus's jets are particularly fast, particularly energetic, that would help explain their extent. But faster jets require more energy, which brings us back to the black hole, to the fuel supply, to the sustainability question. There is also the matter of age. How long have these jets been active? Radio emission fades, plasma cools, radiates away energy, becomes invisible. The fact that we still see the lobes means they are relatively young, still energized, but young on cosmic timescales could mean millions of years. If the jets have been active continuously for tens of millions of years, growing steadily, never stopping. Then size becomes a function of time. Persistence creates scale. But this raises another problem. Black holes are not supposed to feed continuously. They go through cycles, active phases, quiescent phases, flickering on and off. Most radio galaxies show evidence of multiple eruptions, lobes from different epochs. Alcyoneus shows no such evidence, just one continuous expansion, one unbroken flow, as if the black hole turned on and never turned off. This is unusual, potentially unprecedented. It demands explanation. What has kept the black hole feeding? Where is the fuel coming from? Galaxies contain limited gas. It gets consumed. Star formation uses it. Black hole accretion uses it. Outflows expel it. Eventually, reservoirs deplete, unless Alcyoneus is being continuously resupplied. Gas from the cosmic web. Cold flows streaming inward, replenishing what the black hole consumes. This happens, but typically in the early universe, when gas was more abundant. Alcyoneus is not early. It exists in the relatively recent cosmos, where cold flows are rarer, less efficient. The physics says Alcyoneus should not exist, should not sustain jets this large, should not maintain activity this long. Yet it does. This means either our physics is incomplete, or Alcyoneus represents an extreme case, the tail end of a distribution. Rare but possible. An outlier, lucky, benefiting from a perfect combination of factors that almost never align. Both possibilities are interesting. Both teach us something. If our physics is incomplete, we need to revise models, understand what we are missing. If Alcyoneus is just rare, we need to find more examples. Determine how rare, what conditions create these giants. Either way, Alcyoneus is a puzzle, a challenge to our understanding, a galaxy that exists, despite every reason it should not. There is also the matter of age. How long have these jets been active? Radio emission fades, plasma cools, radiates away energy, becomes invisible. The fact that we still see the lobes means they are relatively young, still energized, but young on cosmic timescales could mean millions of years. If the jets have been active continuously for tens of millions of years, growing steadily, never stopping. Then size becomes a function of time. Persistence creates scale. But this raises another problem. Black holes are not supposed to feed continuously. They go through cycles, active phases, quiescent phases, flickering on and off. Most radio galaxies show evidence of multiple eruptions, lobes from different epochs. Alcyoneus shows no such evidence, just one continuous expansion, one unbroken flow, as if the black hole turned on and never turned off. This is unusual, potentially unprecedented. It demands explanation. What has kept the black hole feeding? Where is the fuel coming from? Galaxies contain limited gas. It gets consumed. Star formation uses it. Black hole accretion uses it. Outflows expel it. Eventually, reservoirs deplete, unless Alcyonius is being continuously resupplied. Gas from the cosmic web. Cold flows streaming inward, replenishing what the black hole consumes. This happens, but typically in the early universe, when gas was more abundant. Alcyonius is not early. It exists in the relatively recent cosmos, where cold flows are rarer, less efficient. The physics says Alcyonius should not exist, should not sustain jets this large, should not maintain activity this long. Yet it does. This means either our physics is incomplete, or Alcyonius represents an extreme case, the tail end of a distribution. Rare but possible. An outlier, lucky, benefiting from a perfect combination of factors that almost never align. Both possibilities are interesting. Both teach us something. If our physics is incomplete, we need to revise models, understand what we are missing. If Alcyonius is just rare, we need to find more examples. Determine how rare, what conditions create these giants. Either way, Alcyonius is a puzzle, a challenge to our understanding, a galaxy that exists, despite every reason it should not. One of thousands. We just happen to find it first. Or it might be unique, an extreme outlier, the largest that will ever be found. We do not know yet, cannot know, until we survey everything. The uncertainty is both frustrating and exciting. Every new observation might reveal something larger, something stranger, something that pushes the boundaries even farther. The universe is not static, not fully explored. There are still discoveries waiting, still giants hiding in the data, still mysteries lurking in regions we have not surveyed. Alcyonius proved that. Showed that even with decades of radio astronomy, even with thousands of known galaxies, we can still miss something enormous, something obvious in hindsight, invisible until we learned how to see. What else are we missing? What other structures exist? Right in front of us, waiting for the right telescope, the right survey, the right perspective. The hidden giants are out there. We just need to find them. Alcyonius does not just exist. It affects everything around it. The jets push through intergalactic space, displacing gas, creating enormous cavities, bubbles in the cosmic medium. The scale is difficult to comprehend. Imagine a bubble larger than galaxy clusters, a void carved by pure energy, maintained by continuous pressure from the jets. This is what Alcyonius creates. These bubbles are not empty. They are filled with hot plasma, material from the jets, mixing with swept-up gas from the medium. The temperature is extreme, millions of degrees, hot enough that atoms are fully ionized, electrons stripped away, moving at incredible speeds. The plasma glows, emits radio waves. This is what we detect, the visible signature of Alcyonius' influence. But the bubble is more than just radio emission. It is a physical structure, a region of space fundamentally altered by the galaxy's activity. The pressure inside exceeds the pressure outside. The bubble wants to expand, push outward, but it is also cooling, radiating energy. Eventually, it will reach equilibrium, stop growing, stabilize, or the jets will shut off, pressure will drop, the bubble will collapse, contract, merge back with the surrounding medium, erasing itself. We are witnessing Alcyonius while the bubble is active, while jets maintain the pressure. This is a temporary state, cosmically brief. In a few million years, perhaps a few tens of millions, it will be gone, just a fading remnant. Then nothing. The bubble affects star formation, not in Alcyonius itself, but in surrounding space. Gas that might have collapsed into galaxies is pushed away, heated, made too energetic to form stars. The bubble creates a dead zone, a region where galaxy formation is suppressed. This is called feedback, galaxies affecting their environment, regulating structure formation. We see this in galaxy clusters, central black holes keeping gas hot, preventing it from cooling and forming new stars. Alcyonius does this too, but on a much larger scale, affecting volumes far beyond its own dark matter halo. The feedback might be crucial for cosmic evolution. Without it, gas would cool efficiently, form too many stars too quickly. Galaxies would be different, smaller perhaps, or distributed differently. Feedback regulates the process, slows it down, makes galaxy formation less efficient. This matches observations. Not all gas becomes stars. Much remains in the intergalactic medium, hot, ionized, unable to collapse. Feedback explains this. Jets like Alcyoneus's might be part of the mechanism. There is also the magnetic field. Jets carry magnetic fields. Deposit them in the bubbles. Stretch them across vast distances. These fields persist, even after the jets fade. They thread through the intergalactic medium, affecting how gas moves, how it conducts heat, how it responds to perturbations. Magnetic fields are difficult to measure, especially in intergalactic space, but radio observations provide clues. Polarized emission, Faraday rotation, signatures of organized magnetic fields. Alcyoneus's bubble shows these signatures. Evidence of strong fields, aligned fields, ordered by the jets. The origin of cosmic magnetic fields is mysterious. We know they exist. Galaxies have them, clusters have them. Even the intergalactic medium has weak fields. But where did they come from? How did they get there? Seed fields from the early universe are one idea. Tiny, primordial fields, amplified by astrophysical processes. Jets are another mechanism. They generate fields, inject them into space, spread them across large volumes. If every massive galaxy goes through a jet phase, if they all create bubbles like Alcyoneus, then jets might be the dominant source. The reason magnetic fields permeate the universe. This is speculative, but plausible and testable. With better observations, with more examples, we can determine how common these bubbles are, how strong their fields are, whether they contribute significantly to cosmic magnetism. The bubble also contains cosmic rays, high-energy particles, accelerated by shocks in the jets, by turbulence in the plasma. These particles travel far, escape the bubble, diffuse into the surrounding medium. They carry energy, affect chemistry, ionize gas. Cosmic rays are important for many processes. They heat gas, prevent it from cooling. They regulate star formation. They create secondary radiation. Gamma rays, neutrinos. Alcyoneus is a cosmic ray factory. The jets accelerate particles continuously. The bubble confines them temporarily, then they escape, spread throughout the local universe, adding to the background, contributing to the cosmic ray flux we detect on Earth. Some of those cosmic rays might have originated in galaxies like Alcyoneus, traveled for millions of years, across billions of light years, arrived here, struck our atmosphere, created particle showers, been detected by observatories. We cannot trace individual cosmic rays back to their sources. They are deflected by magnetic fields, their paths randomized. But statistically, some fraction comes from radio galaxies, from jets, from bubbles like Alcyoneus creates. The bubble is not isolated. It interacts with the cosmic web, the filaments of gas connecting galaxies, the sheets and walls of our large-scale structure. The bubble disrupts these, pushes them aside, heats them, changes their properties. This affects how structure forms downstream, how gas flows when new galaxies appear. The cosmic web is not static. It evolves, grows, rearranges. Bubbles like Alcyoneus's contribute to this evolution. They are part of the feedback loop, part of how the universe organizes itself. Eventually, the bubble will fade, the plasma will cool, mix with the surrounding medium, lose its identity. But it will leave traces, enriched gas, magnetic fields, cosmic rays, structural imprints on the web. These traces persist, affect future generations. The bubble is temporary, but its influence is lasting. Alcyoneus is reshaping space, not just occupying it, not just existing, but actively modifying the universe around it, creating a zone of influence larger than anything we thought possible, leaving a mark that will endure long after the galaxy itself fades. To truly grasp Alcyoneus's size, we need comparisons. The Milky Way is our reference, our home, from edge to edge. Our galaxy spans a certain distance. Alcyoneus dwarfs this. The radio lobes alone, one single lobe, is larger than the entire Milky Way, by a substantial margin. This is difficult to visualize. Our galaxy contains hundreds of billions of stars, vast spiral arms, a central bulge, a dark matter halo extending far beyond the visible disk. All of this, the complete structure we call home, would fit inside one of Alcyoneus's radio lobes with room to spare. Now consider Andromeda, our nearest large galactic neighbour. Andromeda is bigger than the Milky Way, slightly more massive, more extended. Astronomers often use Andromeda for scale comparisons. It is familiar, well-studied, impressive in its own right. Alcyoneus makes Andromeda look tiny, insignificant, like a small island in an ocean. The jets extend farther than the distance between the Milky Way and Andromeda, farther than our entire local group, our gravitationally bound collection of galaxies. All of it, every dwarf galaxy, every satellite, every stream of stars, the entire structure, fits comfortably within Alcyoneus's span. This is not just large, it is incomprehensibly vast. Galaxy clusters are the next step in cosmic structure. Massive collections of galaxies, hundreds or thousands of members, bound together by gravity, swimming in hot gas, dominated by dark matter. Clusters are huge. The largest bound structures in the universe. Alcyoneus rivals them, not in mass. The cluster has far more matter, far more galaxies, but in physical extent. In the space it occupies, Alcyoneus competes. Its radio lobes extend across distances comparable to cluster diameters. This is shocking. Clusters are assemblies of hundreds of galaxies, accumulated over billions of years, grown through mergers, through gravitational attraction. Alcyoneus is one galaxy, one black hole, creating a structure of comparable scale through sheer energetic output. The Coma cluster is one of the richest known, thousands of galaxies, a massive concentration near our cosmic neighbourhood, well studied, thoroughly mapped. Place Alcyoneus next to Coma, overlay the structures. The radio lobes stretch across the cluster, touch both edges, encompass the entire system. This single galaxy, through its jets alone, creates a structure as large as one of the universe's great cities of galaxies. Superclusters are larger still, collections of clusters, filaments connecting them. The largest structures that gravity has assembled, the Shapley supercluster, the Laniakea supercluster which contains us. These span hundreds of millions of light years. Alcyoneus does not match superclusters. Not quite, but it approaches their scale, begins to compete, a single galaxy, creating influence zones that touch the realm of supercluster dimensions. This seems wrong. Individual objects should not rival assembled structures, should not compete with collections. Yet Alcyoneus does. The cosmic web itself is the ultimate comparison, the large-scale structure of the universe. Filaments of galaxies, walls, voids between them. The web spans the cosmos, connects everything. Alcyoneus sits within the web, but its jets, its lobes, they extend along filaments, cross voids, reach scales where individual objects blur into cosmic structure, where the line between galaxy and environment becomes unclear. Light travel time offers another perspective. Light from one end of Alcyoneus's lobes takes a certain amount of time to reach the other end. This is not instantaneous, not even close. The galaxy is so large that light, the fastest thing in the universe, requires millions of years to cross it. Information cannot travel faster than light. This means the two lobes are causally disconnected on short timescales. What happens on one end cannot affect the other end immediately. There is a delay, a communication gap. The galaxy is larger than its own coherent scale. Think about what this means. The black hole at the centre. It drives both jets, both lobes, but it cannot coordinate them in real time, cannot adjust one based on observations of the other. The light travel time prevents it. Each lobe evolves semi-independently, responding to local conditions. The central engine provides energy, but cannot micromanage. This is unusual. Most galaxies are coherent systems. Information propagates across them quickly. Timescales shorter than evolutionary timescales. Alcyoneus is different. Too large for coherence, too extended for unified behaviour. It is more like an ecosystem than an organism. Parts interacting, but independently evolving. Human scales are useless here. We live on a planet, orbit a star, exist in a solar system that is invisibly small compared to Alcyoneus. If you could travel at light speed, cross the solar system in hours, the galaxy in years. Crossing Alcyoneus would take millions of years. longer than our species has existed, longer than recognizable human civilization. If we launched a light-speed probe when our ancestors were still in trees, it would not have crossed Alcyoneus yet. This is the scale we are discussing. Distances so large they defy human intuition. Structures so vast that normal comparisons fail. Alcyoneus exists in a realm between galaxies and cosmic web, between individual objects and collective structure. It is both, a single galaxy, yet spanning distances usually reserved for assemblies. This is what makes it impossible. What makes it challenge our models? What makes it so important to understand? Because if one galaxy can achieve this, if the barriers we thought were hard limits are merely guidelines, then the universe is more flexible than we believed, more capable of extremes, more full of possibilities we have not considered. Alcyoneus shows us the universe's range, the extremes it permits, the scales it can reach, and in doing so, makes us question what else might be possible, what other extremes await discovery. Creating Alcyoneus required energy, enormous amounts, sustained over millions of years. Where did this energy come from? How was it generated? How was it maintained for so long? These questions cut to the heart of astrophysics. Energy does not appear from nothing. It has sources. In galaxies, the ultimate source is gravity, matter falling into potential wells, converting gravitational potential energy into other forms. For Alcyoneus, the relevant well is the central black hole, supermassive, containing millions or billions of times the Sun's mass, concentrated in a region smaller than our solar system. Matter approaching the black hole accelerates, falls faster, heats through friction, through compression, through magnetic interactions. The matter forms an accretion disk, spiraling inward, gradually losing angular momentum, eventually crossing the event horizon, disappearing forever. But before crossing, before that final plunge, the matter is incredibly hot, incredibly energetic. It radiates, emits light across the spectrum, from radio waves to X-rays. Some of this energy escapes, floods into space, makes the galaxy's core bright, visible across cosmic distances, but some energy is channeled differently, into jets. The mechanism involves magnetic fields threading the accretion disk. Anchored in the black hole's spin, the rotating black hole twists the fields, creates a dynamo. The fields extract rotational energy from the black hole, from the spinning spacetime itself. This energy flows along field lines, perpendicular to the disk, outward, carrying plasma, creating the jets. The process is efficient. A substantial fraction of the infalling matter's rest mass energy can be converted, not through fusion, not through chemical reactions, through gravitational and magnetic processes. This makes black holes the most efficient engines in the universe, more efficient than stars, more efficient than anything else we know. But efficiency is not enough. You also need fuel. Alcyoneus consumed vast amounts of matter, millions of solar masses, perhaps more, fed into the black hole over millions of years. Where did this matter come from? Galaxies contain gas, hydrogen, helium, heavier elements. This gas can fuel black holes if it reaches the center, if it can shed angular momentum, fall inward. But most gas does not do this. It orbits, stays in the disk, forms stars instead. Getting gas to the black hole requires special mechanisms. Galaxy mergers are one. When galaxies collide, gravitational torques disrupt orbits. Gas loses angular momentum, funnels to the center, feeds the black hole, triggers activity. This is why many active galactic nuclei are found in merging systems. The merger provides fuel, but Alcyoneus shows no sign of recent merger, no disturbed morphology, no tidal tails, no companion galaxy nearby. It appears isolated, undisturbed. So where did the fuel come from? Cold flows are another possibility. Gas from the cosmic web, streaming along filaments, falling directly into the galaxy, never shock-heated, never stopped, just flowing smoothly to the center. These flows can fuel black holes, sustain activity, but they are more common in the early universe. When gas was denser, flows stronger. Alcyoneus is not early. It exists in the relatively recent cosmos, where cold flows are weaker, less effective. Internal processes might help. Gas from dying stars, stellar winds, supernovae. These return gas to the interstellar medium. Some can reach the center, accumulate, eventually feed the black hole. But this is slow, inefficient, unlikely to provide the sustained fuel needed. Another possibility is that Alcyoneus is consuming itself, stars from the galaxy itself, passing too close to the black hole, torn apart by tidal forces, consumed. This happens. Tidal disruption events. We observe them, but the rate is low, not enough to sustain Alcyoneus's activity. The fuel question remains open, unclear, one of the mysteries. Then there is the energy output. How much total energy has Alcyoneus released? Calculating this requires knowing the lobe volume, the plasma density, the magnetic field strength, the age of the structure. All uncertain, but estimates can be made. The numbers are staggering. Energy equivalent to thousands or millions of supernovae. Released not explosively but steadily, over extended time. This represents a significant fraction of the black hole's rest mass energy. A measurable portion of the matter that fell in has been converted to jet energy, then expelled, lost to the galaxy forever. This seems wasteful, inefficient from the galaxy's perspective. All that matter consumed, converted to energy, shot into space, never to return. Why does nature allow this? Why do black holes create jets instead of keeping all the energy? The answer involves fundamental physics. You cannot have accretion without some energy release. Matter falling in must radiate, must lose energy. Otherwise it would just orbit forever. Some of that energy escapes as light, some as jets. The ratio depends on conditions, on the black hole's spin, on the accretion rate, on the magnetic field geometry. Alcyoneus's black hole is configured for strong jets, maximum energy extraction, maximum output. This is rare. Most black holes are less efficient, produce weaker jets, or no jets at all. Alcyoneus hit the jackpot. Perfect conditions, perfect alignment, maximum possible energy output, sustained for maximum possible duration, or close to it. This is part of why it is unique, why we do not see many like it. The energy also affects the surrounding universe, does not just disappear, it heats gas, creates bubbles, accelerates particles, generates magnetic fields. All of this has consequences, downstream effects. The energy deposited in the intergalactic medium changes its evolution, makes it hotter, more ionized, less able to form new structures. This is feedback in action. The black hole regulating its environment, preventing new fuel from reaching it, creating the conditions for its own starvation. Eventually, inevitably, the fuel will run out, or the flow will stop. The black hole will go dormant, the jets will fade. Alcyoneus will transition from active to quiescent. The energy output will cease. What happens then? The lobes will cool, dim, fade from view. The bubble will collapse. The displaced gas will flow back, fill the void, erase the structure. In a few tens of millions of years, perhaps 100 million, Alcyoneus will be unrecognizable. Just another large galaxy. No jets, no lobes, no evidence of its former glory. Unless we catch it now, while it is active, while the energy flows. We miss the show. This makes Alcyoneus precious. A snapshot of a rare state, a brief window into extreme astrophysics, captured at the perfect moment, before it fades, before it becomes ordinary. The energy problem is central. Understanding where it comes from, how it is sustained, where it goes. Answers these questions and we understand Alcyoneus, understand giant radio galaxies, understand feedback, understand how black holes shape the cosmos. The energy is the key, and we are still learning how to read it. Alcyoneus did not start this way. It evolved, grew, became what we see today through a process lasting millions of years. Understanding that process is crucial. Understanding how galaxies become giants, how they create such enormous structures. Then what happens afterward? Galaxy evolution is a long story, spanning billions of years. Galaxies form from collapsing gas, dark matter halos, stars begin forming. The galaxy lights up. Early on, galaxies are small, irregular, chaotic. Mergers are common, collisions frequent. Each merger adds mass, adds stars, adds gas, changes the structure. Over time, through many mergers, galaxies grow larger, more organized. Spirals develop, ellipticals form. The population diversifies, the central black hole grows alongside. Feeding during mergers, during periods of abundant gas, growing massive, millions or billions of solar masses. Most large galaxies have supermassive black holes. This is normal, expected, but most black holes are quiet, dormant, not actively feeding, not producing jets, just sitting, waiting. Alcyoneus's black hole activated, began feeding, started producing jets. This phase is temporary. Most galaxies experience it, but briefly, a few million years, perhaps tens of millions. Then fuel runs out, activity ceases, the galaxy goes quiet again. Alcyoneus is in this active phase now. The jets are on, the lobes are growing, but this is recent, cosmically recent. The jets are young, still expanding, still bright. We are witnessing early stages, or perhaps middle stages. Not the end, not yet, before activation. Alcyoneus was probably ordinary, a large elliptical galaxy, massive, but unremarkable. No jets, no radio emission, just stars, quietly aging, orbiting the galactic center. Then something triggered the black hole, delivered fuel. The accretion disk formed, heated, began radiating. The jets ignited, started pushing outward. At first, the lobes were small, confined to the galaxy's core, expanding slowly, encountering dense gas, high resistance. Progress was limited, but as they grew, as they broke free of the dense inner regions, resistance dropped, expansion accelerated. The jets reached the galactic halo, then beyond, into intergalactic space, where density is low, where expansion is easy. This is when growth became rapid. The lobes inflated, stretched, reached their current size. How long did this take? Estimates suggest millions of years, perhaps 10 million, perhaps 50. The exact duration is uncertain. Depends on jet power, on environmental resistance, on continuous versus intermittent activity. But the timescale is short, cosmically brief, a flash in the galaxy's billion-year lifetime. What triggered the activation? We do not know for certain. No obvious merger, no clear disruption. Perhaps a minor interaction. A small companion absorbed, unnoticed in current images. Or perhaps internal processes. Gas from stellar evolution accumulating, reaching critical density, falling inward suddenly, lighting the black hole. Or perhaps the activation is cyclic, the black hole feeding impulses, long quiet periods interrupted by brief active phases. Alcyoneus caught during one such pulse, larger than previous ones, more energetic, creating the giant structure we observe. What happens next? The jets will continue, for now. As long as fuel lasts, the lobes will keep growing, expanding outward, becoming fainter, more diffuse. Eventually, the fuel will deplete, the accretion rate will drop, the jets will weaken, sputter, shut off. When the jets stop, the lobes will begin fading. No new energy input, just cooling, radiating. The plasma will lose pressure, the bubble will contract, slowly at first, then faster. The surrounding gas will flow back in, reclaim the space, the radio emission will dim, fade below detectability. Within a few tens of millions of years, Alcyoneus will be invisible to radio telescopes, just another galaxy. The optical appearance will not change much. The stars are unaffected by the jets. They continue orbiting, aging, dying, forming new generations. The galaxy itself persists, but the radio giant dies, becomes a relic, invisible, forgotten. Unless we observe it now, document it thoroughly, study it while it lasts. Future astronomers will not see Alcyoneus. They will see a large elliptical, massive, unremarkable. No hint of its former glory, no evidence of the jets, no trace of the lobes, just stars, orbiting, quiet. This is the fate of all radio galaxies. The active phase is temporary, a moment of violence, then silence. The universe is probably full of dead giants, galaxies that once had enormous lobes, now faded, invisible, forgotten. We only see the currently active ones, the lucky few caught during their brief moment of visibility. This biases our understanding. We think radio galaxies are rare, but maybe they are common. Maybe most large galaxies go through this phase. We just miss it most of the time. Timing matters. Alcyoneus might represent a common evolutionary stage, not an outlier, not a freak, just a normal part of the life cycle, captured at the right moment. Or it might be unusual, an extreme case, rare configuration, perfect conditions, unlikely to repeat. We cannot tell from one example, from one giant. We need more examples, more observations, statistical samples. Then we can determine how common this is, how it fits into galaxy evolution, what role it plays, whether it matters for the broader population, or whether it is a sideshow, interesting but irrelevant to most galaxies. The evolutionary question is fundamental. It asks not just what Alcyonius is, but what it was, what it will become, how it fits into the grand story of cosmic evolution, of structure formation, of galaxies growing, living, dying. Alcyonius is one chapter, one moment, in a story spanning billions of years. Understanding that moment, that chapter, helps us understand the whole narrative. Every extreme object is a natural laboratory, a test of our theories, our models, our understanding. Alcyonius is no exception. It teaches us several things, some expected, some surprising. First, size limits are not hard boundaries. We thought there were maximum scales, beyond which structures could not grow. Alcyonius exceeds those scales, shows the limits were artifacts of our observations, our limited sample size. Not physics. This means other limits might also be soft. Other supposedly maximum values might be surpassed. We should be cautious about declaring things impossible. The universe is more flexible than we give it credit for. Second, environment matters profoundly. Alcyonius sits in a void. Low density, low resistance. This allowed the jets to expand farther than in dense regions. This tells us that giant galaxies preferentially appear in underdense environments, that the cosmic web structure determines where giants can form. This has implications for surveys, for where to look, for how to find more examples. Third, black hole activity is not well understood. We thought we knew the duty cycle, how long black holes stay active, how often they turn on and off. Alcyonius suggests longer active phases are possible, more sustained feeding. This requires revising models of black hole growth, of accretion, of fuel supply. The black hole is less intermittent than we thought, more capable of sustained output. Fourth, feedback is more important than we realized. Alcyonius affects a volume far larger than its own galaxy, heats gas, prevents star formation, deposits energy across vast regions. This is not local feedback. This is large-scale environmental modification. One galaxy, affecting structure formation across volumes usually associated with clusters. This means individual galaxies can have outsized influence, can regulate their surroundings far beyond their immediate neighborhood. Fifth, radio surveys are incomplete. We have missed giants, probably many giants, because our surveys were not designed to find them. This is a technical lesson, but important. It reminds us that discovery depends on how we look, not just where. LOFAR found Alcyonius, not because it appeared recently, but because LOFAR looked differently. Sensitive to extended emission, wide field. This tells us that other surveys, other wavelengths, other techniques, might find other populations, other classes of objects, hiding in plain sight. Sixth, rare does not mean unimportant, even if Alcyonius is unique, even if we never find another. It still teaches us about possible extremes, about the limits of physical processes, about what the universe permits. Outliers are valuable. They probe parameter space, test theories in regimes we cannot access otherwise. Alcyonius is an outlier, but an informative one. Seventh, magnetic fields are crucial. The jets require magnetic fields, strong fields, organized fields, maintained over vast distances. This tells us magnetism is not a minor effect, not a small correction, but a fundamental player in galaxy evolution. In jet physics, in cosmic structure, we need better magnetic field observations, better models, better understanding. Alcyonius demonstrates this need vividly. Eighth, timescales are longer than we thought. If Alcyonius's jets have been active for tens of millions of years, that is longer than typical estimates, longer than most models predict. This suggests black holes can sustain activity longer, that fuel supplies are larger, or replenishment more effective. This affects predictions for black hole growth, for quasar evolution, for the high redshift universe. Ninth, the universe is still surprising us. After decades of radio astronomy, after thousands of galaxies observed, we can still find something completely unexpected, something that challenges assumptions. This is humbling, exciting. It means we have not figured everything out. That discovery continues, that the universe retains mysteries. Alcyonius also raises questions. It does not answer everything. It poses new puzzles. Why this galaxy? Why now? What is special about its black hole? Its history? Its environment? We do not know. Cannot know without more examples, without comparative studies. The questions drive future research, guide observations, shape theoretical work. This is the scientific method. Observation. Question. Hypothesis. Test. Repeat. Alcyonius observed. Questions posed. Hypotheses forming. Tests being designed. The cycle continues. What will we find? More giants. Probably. The southern sky remains largely unsurveyed. New telescopes will reveal more. Dozens, hundreds perhaps, each adding data, each constraining models. Eventually, we will understand how giants form, how common they are, what they tell us about galaxy evolution. But for now, Alcyonius stands alone, the largest known, the most extreme, a monument to the universe's capacity for scale, for energy, for structures that defy easy explanation. It exists, despite our theories saying it should not, despite size limits, despite energy constraints, despite all the reasons it seems impossible. It is there, real, observed, measured, teaching us, challenging us, reminding us that the universe is bigger, stranger, more capable than we imagine. Alcyonius is not just a galaxy, it is a lesson in humility, in wonder, in the endless capacity of nature to surprise. We thought we understood radio galaxies, thought we knew their limits, thought we had seen the extremes. Then Alcyonius appeared, larger than thought possible, extending farther, lasting longer, affecting more, showing us we were wrong. Not completely wrong, but incomplete, missing something, underestimating. And that is valuable. That is how we learn. By being wrong, by finding exceptions, by discovering that our carefully constructed models, our well-tested theories, our confident predictions, are approximations, useful, mostly correct, but not complete, not final, not perfect. Alcyonius is a crack in our certainty, a giant standing at the edge of possible, showing us there is more to learn, more to discover, more to understand. The universe is vast, full of giants, some we have found, many we have not. Alcyonius is one, the largest known, but probably not the largest that exists, just the largest we have seen so far.